Hey everyone, today what we're going to be going over. Hey everyone, my name is Dr. Clyde Letzum, and today what we're going to be going over is resonance in a single-ended air column. Alright, so this is an experiment that we do in our lab. We have in the experiment, we have an air column and a piston at the back which is adjustable, and a speaker that's going to generate a sound inside of the air column. The idea is to adjust the piston such that we find resonance within the air column, the location that will give us resonance, within the air column. And so what we do is we generate a sound from the speaker, okay? And that sound will actually go down to the end of the air column where the piston is. And because there's no way for the sound to escape, it will actually bounce back to the speaker. And again, the idea is to adjust the piston such that we get resonance. In this case, resonance will be represented to us by the loudest sound coming out of the air column. And the reason why it's the loudest sound is because the sound that actually goes down the air column and bounces back is going to create a set of constructive and destructive interference patterns within the air column. And what we want is the sound that's at the edge here to actually create the most constructive interference at the end, causing that loud sound to come out of the air column. All right. So to understand how this actually works, what we're going to use is we're going to use traveling waves, and we're going to use transverse waves in order to Hey everyone, this is Dr. Clyde Letzum, and today what we're going to be going over is resonance in a single-ended air column. And this is an experiment that we actually do for our lab, where we have an air column, and at the one end of the air column we have a piston that's adjustable that you can move in and out of the air column, and at the other end we have a speaker. Now the idea behind the experiment is to find the locations of resonance, or in other words, to adjust the piston such that when this speaker creates a sound, okay, that sound goes to the back of the air column here where the piston is, and it bounces back and creates a loud sound coming from the air column. When we get that loud sound, that means we have resonance at the edge here, which means we have the most amount of constructive interference at the end of the air column over here. Now, when we actually send that sound down the air column and it bounces back, what happens is we get a set of constructive and destructive interference within. But again, our objective is to get the loudest sound coming from the end of the air column here, which means we have the most amount of constructive interference. To understand how this happens, what we're going to do is we're going to use traveling waves and standing waves to do so along a string. So for now, let's consider this. We're going to think of this as being a string that's actually connected to the back of the piston here. And what we're going to do is we're going to move the string up and down at a regular or constant frequency. Okay, when that happens, all right, so we adjusted it to this location here. When that happens, what we're going to get is, again, a wave that travels down and a wave that travels back, and it's going to create a standing wave, okay, along the string. Again, it's connected here. It's going to create a standing wave along the string that looks something like this. Now, what you'll notice is that at the edge of the air column here, we do not have the maximum amplitude in the string. So if we're thinking about this as sound, what this means is we're not going to get the loudest sound coming out of the air column if given the frequency that we're generating here, okay, and the distance within the air column, because it doesn't match up as it relates to our string here, that means we're not going to get the loudest sound coming out of the air column if the position, again, of the piston and the frequency at which we're moving the string up and down is at what it's currently at. So what we can do is we can adjust now the piston such that the distance from the piston to here is approximately what is shown on the screen. Again, if we create the same frequency down the string, eventually what we're going to get is we're going to get a wave that bounces back, and it's going to create, along with the wave that the waves that we're sending, it's going to create a standing wave pattern within this string. And you'll notice now this time the largest amplitude of that standing wave is actually at the very edge of the air column, which means then that we found the location where we'll get first resonance. Okay, that loudest sound coming back, the sound that's going to be have the most constructive interference at the edge of the air column here. Okay, that location where we have our loudest sound, or in the case of the string, the largest amplitude, that's going to be equal to, we're going to call it L1 for now. And if you notice, that L1, okay, is equivalent to 1/4 of a cycle of that wave. Okay, and similarly, then it's equal to 1/4 of the wavelength. If we were to move the piston to the back now, a little bit further back, such that we find the area of second resonance, that area of second resonance, okay, in this case, again, we have the string. We're moving that string up and down at the same frequency, okay, at the same frequency. We're going to end up getting same frequency and constant. We're going to get a standing wave pattern that looks something like this. Okay, again, you'll notice here that the largest amplitude is created at the edge of the air column. Okay, which means that if we move the string up and down at the constant frequency and that same frequency and a given frequency, that sound the string goes down the edge of the goes into the air column and comes back. In this case, what you'll notice, we get the largest amplitude, which means then we have just found our area of second resonance. Okay, so our area of first resonance was here, and our area of second resonance is here. And what you'll notice about our area of second resonance is equal to that 1/4 of a wave from L1. And it's now equal, and if we add that to half of a cycle here, okay, half of a cycle, we end up then with our location of second resonance. So our location of second resonance is approximately equal to 3/4 of the wavelength of that specific frequency that is generated when I move the string up and down. Okay. Now, if we go now and let's move the air column, the piston again further back, and we create a traveling wave going down the string. Okay, and again we remain at the same frequency. We're keeping that frequency constant. What will happen is, again, we'll get a traveling wave going down the string. It will bounce back, and eventually we will get a standing wave pattern that sort of looks like this. Again, you'll notice the largest amplitude is at the edge of the air column, so that means that we've adjusted the piston enough that we have now found our third location of resonance, okay, or the third location that will allow us to get resonance at the edge of the air column here, which means now we're going to get the maximum amount of sound out if we're talking about sound waves. All right. And that third location, if you notice, we have within the air column, we have one full cycle, okay, or one wavelength plus 1/4. So that means now that location now is going to be equal to 5/4 of a wavelength. Okay, it's equal to 5/4 of a wavelength. And we can see again, this is 1/4 plus a half plus another half. This half is equal, this half plus this half is equal to one full cycle or one full wavelength, and plus that quarter now gives us the 5/4. Now looking at all this mathematically, all right, if we want to find the area of first resonance again, that area or that location of first resonance within the air column is going to be equal to lambda divided by 4, where lambda represents our wavelength. So for whatever frequency we're generating, lambda related to that frequency divided by 4 is going to give us our L1. If you remember, for L2 is half a wavelength plus a quarter, right? So half a wavelength plus a quarter, which ends up giving us 3/4 of a wavelength, is the location where, if we put the piston at that location, we're going to get our second resonance. Okay. Now for the third resonance, remember we had an entire wavelength, right? And that entire wavelength here is represented by lambda plus the quarter from L1, right? So that's lambda divided by 4 plus that plus the full wavelength. We add those two up together, common denominators. We end up with 5/4 lambda for where L3, the location where L3 would be. Okay. If we look at the three equations that we have here, or the three locations of resonance, right? L1, L2, and L3, we can actually develop an equation, all right, to represent those three locations, or any location where we would get resonance, whether it be first, second, third, fourth, fifth, or whatever. That equation is equal to n lambda divided by 4. And again, this is for a single-ended air column. That location is n lambda divided by 4. Okay, so any location we can get, we can use this general equation here in order to get it. All right, and that will give us again our first, second, third, fourth, so on and so forth, resonance, location for resonance. Okay. All right. So now let's say you're given an experiment where you need to actually figure out where those locations are. What you can do is you can actually calculate that location, the approximate location, based off of these set of equations. If we're dealing with sound, okay, we know that the speed of sound is actually equal to 331 meters per second plus 0.6 times the temperature which the sound is passing through. For the purposes of our experiment, we're going to assume that temperature is approximately 25 degrees Celsius within our room. If we know that velocity information, and we know the frequency at which we're generating from the speaker, okay, we can actually figure out what lambda is by using this equation. And we can manipulate this equation here such that we get the velocity of sound divided by the frequency being generated, or the frequency of that sound, will end up giving us lambda. Once we've calculated that out, we can take now the information we learned from the examples before, and we can say, well, our location where we would get first resonance is going to be equal to lambda divided by 4. Okay. The area the location where we're going to get second resonance is going to be 3 lambda divided by 4. And the location where we're going to get the third resonance is going to be 5 lambda divided by 4. Okay. All right. So that is how we'd find theoretically now what our locations for resonance are. Now, experimentally, what we can do is we can move the piston to that approximate location, and then use the following equations then, okay, in order to see if, once we find those areas of resonance, to see if we can find what the theoretical velocity is for sound. And we can do that by using the equations that are actually listed on here. Okay, so you can find them for first resonance against second resonance and so forth. All right. So This, again, was a discussion on resonance in a single-ended air column, and this is the experiment that we will conduct in our lab. Maybe you have some that you do in yours. And again, my name is Dr. Clyde Letzum. If you want more information about me, you can go to my website. You can subscribe to my YouTube channel, and if you like this video, go ahead and give it a like. I'll see you guys in the future.